quick, does anybody know what zoned namespaces are? Have you heard about it? Okay. Open-Channel? So maybe more people. Okay, so I'm going to go a little bit, it's been a long road since we started talking about Open-Channel, never got standardized. Now we're bringing it to NVMe. And what I want to talk about today is a little bit about, what we are with the specification, how it works, but mostly what are the use cases, because most people today are talking about archival use cases, how we're going to adopt a QLC memory, how we are going to build on top of the technology that SMR drives us build, and that's a very important use case. But there are other use cases that we see in zoned namespaces that I'll try to convince you are also important. So starting a little bit, the first question is, why do we even need a new interface? So why do we start looking at things that are different from a read-write interface? And there are three things that I think are kind of important to consider. The first one is, if you look at a system level, if you start down to the SSD, an SSD is basically a log-structured device that puts data that comes random and tries to structure it into sequential writes and put some metadata on the side. If you go up the stack, you have file systems that are doing exactly the same thing. Many of them. You have examples in Linux, F2FS, XFS, CFS. They basically do the same thing. Instead of doing it at an LBA level, they're doing it at a sector level, or at a larger segment level, right? And if you go down to the application, you have applications that start trying to do the same thing because they want to be flash friendly. So you end up with this thing that is a log and log problem, which basically means that your application thinks you're writing sequential, but at the end of the day, you're running completely random on the device, so you're not actually helping that much the algorithms inside of the SSD to do proper garbage collection. So we're playing this game of hinting back and forth to try to make good decisions. The first, and obviously, new interfaces that we're trying to do is to remove these redundancies and try to leverage these log structures end to end, from all the way from the application, maybe the file system, all the way to the SSD. The second thing is that there has been a huge cost gap between HDDs and SSDs. It's lower today, but it's still significant, so that people would not hop all the way into NAND. So everything that people that want to adopt flash to try to differentiate themselves, they try to minimize cost as much as we can, right? So introduction of QLC is important, but at the end of the day, if you look at the SSD design, there are some barriers that are still there. If you want to maintain a 4 kilobyte mapping table, you have that 1 gigabyte per terabyte boundary. If you're putting a 64 terabyte SSD out there, how much are you paying in DRAM? So how can we reduce that cost to even more bridge the gap? And then the last thing is a little bit, building what Andy was saying. We have containers, multi-tenancy is everywhere, especially as we grow these capacities. It's very normal that we have all these applications running on the same SSD, even though if you don't know that. So what is mainly known as the neighbor problem, noisy neighbor problem, applications, 100% reads, interrupting 100% writes, how do we address that? So now we've looked a little bit at the problems. I'm going to deep dive into the zone basic concepts, and then I'm going to come back to the use cases once you have these concepts in mind. And by the way, you're very welcome to ask any questions, so that, I really want you to get this. So if there's any term I'm using that you don't get, please, ask. So zoned namespaces is basically a way to divide the SSD into same size zones. So you're taking the LBA space, the whole address space, and you are dividing in different zones, and those zones are tied to a state machine. So that's basically, you can see if you're familiar with Flash, it's very like the way Flash works internally, right? So you write at this LBA sequential within the zone, you need to write sequential. When you filled up the zone, you need to reset the zone to come back to the point, so you don't need to do garbage collection internally, because all the data is being managed by the device, by the hosting itself. So when you lay out the zones in this address space, you can lay it in different ways. So, and I have a couple examples, and we're going to get more deep into that in all the slides. So, one configuration can be that you have zones that go across all your NAND arrays. So those are huge zones. You don't have any visibility about the parallelism. The zone is managing the parallelism of the NAND. Another possibility is that you have zones that are vertical. So you have zones that are to 1 die or 2 dies of the NAND, another zone that goes maybe 4 dies of the NAND. And that way you can manage a little bit more what is the parallelism on the device. So basically, dividing the address space into zones, managing from the host how the zones are operating. So you need to write sequential to the zones. You have some states. This is, I put it for completeness. It's not really important now. You write to the zone, you open the zone. Whenever you finish the zone, you close the zone. But the important part is that the host is the one that needs to reset the zone to the initial state. The second thing that is a basic concept that is coming into zone namespaces is that if you think of the first configuration I was talking about, where the zone goes across the whole NAND array, is that you are not having anymore when you're writing a sequential on a device, NVMe doesn't guarantee you any ordering. That means that if you need to respect that you write sequential within a zone, you need to respect write pointer. Since you don't have any ordering, that means that if you have a queue depth higher than 1, you risk that one IO arrives before the other IO, so suddenly you're breaking the sequential write rule. There are different ways of solving this. When you have a zone that goes across the whole NAND array, you definitely want to have queue depth higher than 1, because otherwise your bandwidth is going to be the bandwidth of a single NAND device, right? So what we're doing in NVMe is one of the proposals that is getting into the spec is to use something that is called append command. So if you're familiar, there was a paper from UCSD that is the nameless writes. That is basically, you send a write that is anonymous, and then the device puts the LBA on the write, and the device returns it back. So append command is a specific implementation of this nameless write scheme. So in the zone context, that basically means that if you are an application, you can say, I want to run to zone 5, and I send a bunch of IOs without knowing to which a particular LBA I'm writing to. And then the device is selecting which LBA that is going to, and then it comes back. That gives you basically that you can have a higher queue depth, and that you don't need to take care of your write pointer. Does this make sense? I see some faces that okay. So this is very good when you have these large zones. The main problem of this is that it is very good from a device perspective, but it's very challenging from an application or a file system perspective, because we have some customers that have file systems that do snapshotting, for example, or end-to-end encryption, and not knowing the LBA in advance completely changes how this logic works. And I don't want to say this is good or bad. It's good for some people, but it's challenging for some other people. And we're looking at some other ways of solving the same problem with something that is transparent for the application. So up until this point is what, so I cannot really talk about what are the specific about the TP. I know that many of you are in NVMe, so maybe you know about that already. But this is basically what is going into what we're calling the Zoned Namespaces TP. That is a technical proposal in NVMe. What this means is that the host, with this basic concept, the host starts having more responsibilities. So it's not only a read-write device, it's a device that has to manage read-write, it manages the append if you're implementing that, you need to manage the reset of the zones, and then you might have to have some other states, you might want to transition to other states in the state machine to manage your internal resources. That's maybe going to specifics on the TP, but it's a little bit more complex. And I try to map a little bit from this log-on-log problem what's going to happen on the host side, right? So on the host side, you're going to have what you have been doing of your data placement, your address mapping to which part of the address space, your namespace you're writing. You're not going to have to think about zones. So you're going to do data placement at a zone granularity. You're also going to do garbage collection on the host. That means that you probably want to reuse part of the garbage collection that you're using already for your log structure, whatever application or database, and you're going to have to map that to understand zones so that you don't do garbage collection 2 times. I mean, the worst thing you can do here is trying to put a SIM layer to abstract the zones because then you don't get any benefit. And then you're going to have to manage this zone metadata, which is very similar to the way you're managing your internal metadata for your file system segments or your SS tables if you're doing something like RocksDB or something similar. So until here is what basic CNS is. And it builds very much on top of SMR technologies from hard drives. So if you're familiar with SMR, SAC CBC, T10, T13, this sounds very, very familiar. What we're trying to do now is bring in some new TPs into NVMe to address some of the challenges that I just described. And the first one that we're bringing is this that we're calling some random write area. And let me explain it first, and then I'll go to why we really want to do this thing. So I told you before, when you have a zone, you need to write sequentially into the zone. That means that even if you have a log structure file system, many times it happens that you're writing sequentially, and at some point in time, you're going to have some metadata that is extended. And that metadata might be updated at some point. If you move completely to Zoned Namespaces, that means that you maybe need to do log updates to your metadata, and at some point in time, you're going to need to do some garbage collection on your own metadata. Meaning that if you are tiring your storage system and then you have very cold data, you're basically introducing write amplification, yes, by the way, you're writing your own metadata. The good thing is that this type of metadata is very well identified. So people that are building all-flash arrays, you know exactly where that metadata is placed. And you can tell us, to vendors, hey, I know that I have this few kilobyte window where I really need to go back in time. And this is exactly what the zone random write area is doing. It's basically exposing you the cache that we have inside of the device and letting you manage that. So when you are writing to a particular zone, you have a window where you can do in-place updates down up until the moment you want, and then when you know that that data is immutable, then you can do a commit and flash the data. And this helps very much in terms of write amplification. So that's one of the main use cases. But it also has this particular property, and is that since you're allowing to do in-place updates, you're also breaking the write pointer. And that means that you can actually send several IOs to several queues in flight to the device, and then suddenly you're solving the same problem that the append command is trying to solve transparent to the application. So if you balance your system, I'm implementing this in TLC, obviously your cache has to be a little bit higher because you have more bandwidth on the backplane. If you're doing QLC, you might leave out with a little less. It's all about balance, but we have experience with this being able to saturate the NAND without making changes to the application. And then, there's a couple of details that are a little bit important. The way you do the commits is that we have an interface that allows you to do these explicit commits. This is important because one of the things that people want to do with these zone devices is open hundreds of zones at the same time. And that puts pressure on the resources that we have on the device. So one way of managing, try to close this zone so that you can free up zone resources is letting you do these commits explicitly. So maybe you reach at the end of your file system segment, and then you want to commit the data and then transition the zone to a different state. This is still very much in the discussion, but we have the semantics allow you to do that. If you're having a fully sequential workload and very fast updates and continue, you can also do this sort of implicit commit. Whenever you go out of the window, we will do the commit for you, and that's how you would get the highest throughput. But as we know, throughput is not everything, right? So we have these two trade-offs. So this is the first thing. The second thing that we're working on is simple copy. And when I say working on, it's with my NVMe hat. So there are many places. This particular TP is being driven by NetApp. So it's many people contributing to that. And this is called simple copy. If you're familiar with SCSI, Xcopy. And the reason to call it simple copy is because Fred Knight, who also worked on Xcopy, said, I really want something that gets implemented this time, so I'm going to make it simple. So this is a very, very specific use case. It's being standardized as a global NVMe, so you can use it in any NVMe device, but it's definitely having its root use case in some namespaces. And the idea is that since you're doing garbage collection on the host, then suddenly it might be that you need to control where your valid data is within zone, right? So you need to move data around. The problem is that in a normal SSD, the device is doing it within the controller, but since the host is handling the metadata, you would initially have to read the data through your fabric, PCI interconnect, all the way to your CPU root complex, to then write it again. So this command basically allows you to just point to the data that you want to move around and offload it to the controller. So it's a pretty simple idea, but it's, it would allow us to reduce some of the problems that might come with doing a host-driven garbage collection. We're doing it in such a way, and this is the reason that it's simple, that you can select as many LBA ranges in different zones as you may like. You form an SGL, but that's the source, but the target is a single LBA range. And we're reducing that to a single controller and namespace in NVMe. I know that some people really want to see this across different devices, especially people that are doing computational storage, because you probably want to go through your NIC and then copy data all the way to your SSD without going through the CPU. There are many people we're also doing work in that space, but at least it's not the way the first TP is going to NVMe. But if I'm sure at some point it's going to happen. The good thing is that I hope that this time we really get the patches upstream in Linux, because it's been like, I don't know, 15 years. So now, I think now you know everything that is to know about CNS. I'm going to come back about the use cases, right? So the first use case is pretty obvious, is what we're all promoting to start with, is the archival use case. It's basically you have your infrastructure for SMR drives, you want to start adopting a QLC memory, you have semantics that are very, very similar. There are many things that play here, but the main thing is you reduce cost. And you reduce cost in several ways. First of all, you reduce the write amplification. So you target a write amplification of 1 on the device. Might not really be 1, might be 1, 6, 7 zeros, and then some blocks die, but it's very minimal compared to what we see today. The other thing is that since the host is managing where data is being placed, we can really reduce the over-provisioning. So we don't need to be able to maintain a steady state. We don't need to allocate a 20% or an 11% or even 7% of the device. To do this, we can really expose all the flash to the host, and then let the host and those data structures manage that. The third thing is that, in my thing I mentioned a little bit about, is that the device does not anymore need to do a 4 kilobyte mapping, it does a zone mapping. So that means we're breaking the 1 gigabyte per terabyte DRAM usage. And we can really reduce the cost in that end without any penalty. And then, endurance is everything when we go to QLC. So this technology helps to treat QLC memory in a very, very nice way. So you will get more endurance out of it. And that definitely helps gaining adoption. We see that as tiring for cold storage. You would get CNS SSDs probably as your cold but not so cold data. Probably you will continue using hard drives, and people is innovating with dual actuator and HMAR and all that. So hard drives are still bridging the gap and innovating, so those are still going to be used. And tape is apparently coming back, so well, never left, but it's still being very much used, so it's still going to be there. And if you look at the coming back, how the zones are being laid out on the device, and this is important for the next use case, is that zones on this archival use case, you want them to be as large as you can. So it might go through the whole NAND array. It might even go vertically some other blocks, so that you have less metadata because it's data that is more immutable. So you can reduce the management on the device by doing it this way. The problem is that when you run applications that go on top of these devices, you have no control over the predictability, because those guys eventually are going to run into the same physical device, physical NAND blocks, right? So you're going to still see these noisy neighbor problems. You're going to see, we do a lot of things on the device to solve these issues, but those issues exist, and in this particular configuration, you will still see those issues. The second use case I want to talk about, which comes very much from the open channel use cases, is using zones as a way to enable multi-tenant applications and deliver higher predictability. And the concept is pretty simple. Is, well, instead of thinking of zones as very large, probably laid out on QLC memory, why don't we use them as a mechanism to split out the device, which are very large either way, and then given the possibility to put different applications on different parts of the device. So very few people are consuming all the bandwidth, especially as we move to Gen 4, on a single application. So you can really go and split this from your software management perspective. And what this is giving you is basically that you are having these isolation domains within the zones. And in NVMe, we have this concept of endurance groups and NVM sets. You can build it on that. You can build it on a different way because not everybody wants to have, if you have a very large device, if you go to an extreme, you might end up with a, 256, 512 of these namespaces. You don't want to manage 512 namespaces. Maybe we want to have these isolation constraints on the zone data structure in itself. But the important thing is we still inherit a lot of the benefits from the archival use case. We reduce write amplification because the host is the one that is managing the data placement. We reduce the over-provision. We reduce DRAM. Obviously, we consume a little bit more of DRAM because we don't have very large zones. We have small ones, but it still is nothing compared to what a 4 kilobyte mapping table looks like. But at the same time, we're gaining this possibility to do I/O isolation on different zones. And this is very important, especially for cloud customers. So do you have any questions up until here? So because from now on, talk about Zoned Namespaces, go to the use case, and now I'm going to talk a little bit about the ecosystem that we're building in Linux and how you actually are going to consume these devices. So, cool. So it all starts, so here I'm going to go through a couple of slides. It all starts with the ecosystem that was built for SMR drives. And here, people like Seagate, WD, SUSE also helped a lot, build this ecosystem that is called the Zone Block framework that lays on top on the block layer. And what basically allows you is that, right now it's only support for SCSI and other drivers, but basically the block layer understands that there are some, the LBA space is partitioned in zones, and it's posing all the way up to the application. It also exposes to file systems, and actually today F2FS already supports these zone devices natively. So it maps these segments to the zones, and then you can do, you can see that it reduces write amplification when you do some measurements. We already have the patches by WD on ButterFS, and I'll show you later on. We are all working on different file systems. Damien from WD also pushed recently, I think he's in V5 or V6, for something called ZoneFS. That is basically a file system that statically maps zones to files. So it might simplify the way you are implementing zone adoption, at least for smart drives. We'll see for CNS how we look at it. But the important thing is that the framework is almost there. So it's not like when we started implementing the whole Open-Channel stuff that it took us like 2-3 years to push the basics. The basics are there, so CNS adoption is going to really go much faster in terms of ecosystem. So building on top of that, here's a lot of things. I'm going to focus only a couple of them. We are basically modifying all the parts that already understand the zone framework to understand CNS. So obviously we need to implement the NVMe driver, but that's pretty simple. Adapting the block layer is not that big of a challenge right now. We need to add a couple of commands and a couple of knobs for CNS, but the basics are there. F2FS already has support. We obviously need to do some work there because one of the main differences between SMR drives and CNS is that SMR drives have this thing called conventional zones. That's basically there is a number of zones where you can randomly write to. And that's where all file systems are using to store their metadata. We don't have that in CNS. You can say, well, you can ship a drive that has a conventional namespace and a CNS namespace. Yes, we can do that. Probably do that, but some people don't want to do that. So we need to make sure that we support people that only want to deploy CNS drives. So we're trying to do this that I described before, like log structuring everything on the metadata side for people that really want to do that. We're adding support for new interfaces too. Things like IOURIN that got merged like a year ago, 9 months ago, adding support for these new commands too. And then, the rest of the ecosystem in terms of tools, it also requires a number of changes. One thing that I want to talk about that I'm going to focus after on the next slide is a library that we call XNVME, which is, one of the problems that you see when you start having these new interfaces is that you're not talking to a block device anymore. So sadly, when you have an application, you need to modify part of the application. And this has always been a problem because you modify an application, what happens, people tend to modify to use SPDK, people really deploy these things, and then you are tied to SPDK for the rest of your life. If you want to use a new interface, it might be problematic. If you want to expand it to other applications, poof. So that has hindered adoption very much. So what we're trying to build is this library. I'm going to go one slide and then I'm going to come back. That we call XNVME, which is basically a user space library that offers you an interface for non-block devices. And the idea is that it sits across different file systems. You can run it through the kernel path. You can run it through your normal pread, write. You can go through libIO. You can go through IOURIN. It also has a backend for SPDK. You can we even have a backend for FreeBSD. We have some customers that want to use it in FreeBSD. And the idea is that once you need to rewrite your application, and if CNS has to succeed, some applications will need to be rewritten. So we're trying to minimize the effort that these applications need to make. And right now we're building a prototype with RocksDB where we can see that the changes we're building on RocksDB are very minimal when most of the logic is going to the library in itself. Another thing that is that this library allows to, which is very interesting, is that since it is abstract in the way you write to the device from the metadata that you're storing, so one of the problems even when you don't go to CNS is that people that want to use raw devices on databases have the problem that when you deploy that, your administrators are going to tell you, I want to use file system semantics because how I'm going to use this thing. I have a number of scripts that use all these tools, and this doesn't support it. So what we're building on top of XNVME, and it is allowing, is to build a very thin user space file system. You can build it on top of Fuse, or you can build it on top of SUFS, that is what NetApp is developing for zero-copy user space file systems. That is kind of a fake file system. It looks at the metadata and presents data that is on a raw device or a CNS device with file system semantics. And this really helps the way you can adopt this and use the tools that you're very used to without without compromising on how you are managing the storage from your application. If some of you are going to FAST or Vault in a month, we're going to have a tutorial and a talk dedicated to XNVME there. So if you're interested, you can go and talk, see that. I'll come back. We are, apart from XNVME, we also, I mentioned about the different tools. One tool that I really want to mention too is that we're making a lot of changes to FIO. FIO already have support for SMR drives, but the problem is that when you're putting an SSD, probably with TLC, you really need to make sure that you get the most out of the device to measure the actual latency and performance. So we're doing all that code, and we're obviously open sourcing it in the moment that CNS is being ratified. Last thing I want to mention about is QEMU. So NVMe started with a pretty good implementation of QEMU when NVMe drives were not out there very much. I think it has been a little bit left aside. We're picking that work up, and we've rewritten most of the QEMU NVMe driver to make it available for people. So when you're trying these new interfaces, we do all our development on top of QEMU. It's much easier. And we already started pushing all the patches for NVMe 1.3, 1.4 compliance. I think Keith already put the act yesterday. So in the moment that we are putting CNS out as a TP, we'll put the patches, and that I hope will enable most of you to test your applications on a virtualized or emulated environment. So, I'm going back. So said that, and I'm 4 minutes. That's pretty good. So a few takeaways. I believe after all this road talking about new interfaces coming from the Open-Channel days, I think now it's happening. So CNS is getting into NVMe. One of the things that is also helping is that the way we're standardizing CNS is not CNS on its own. There's a number of work that is going around to refactor NVMe to adopt new namespace types. And that's very interesting. Samsung has key values, so we definitely want to use that. But as we bring new things like computation or storage, when it reaches NVMe, it will most probably go on top of this framework. And it is very good to see that because when you don't have this namespace tab concept, it's very messy when you implement that. When you have it in place, it simplifies very much how you structure your application or your file system. It's been driven by a number of vendors and a number of early customers, so there is no single vendor lock-in. So I think most SSD vendors will be building that, so which is a very good thing. In terms of use cases, archival is the use case that gets thought of first, but we do believe the area of predictability is something that can come with CNS, and those are part of the TPs that we're working on to bring more features in this end. The host needs changes. There's no way around that, but most of the changes are already there. And people like Microsoft have shown that you can actually deploy SMR drives on the data centers. So I don't think there is a big leap of faith believing that this thing is going to reach a significant adoption. For the changes, some changes are going to be more significant if you try to do a pen command. Some changes are going to be more easy to adopt, and that's where we're bringing things like the some random write area. And we're building an open ecosystem. So I know Samsung maybe has not been the most active participant on the Linux community, but we're changing that. We opened an R&D center in Denmark a year ago, and our sole mission is to contribute to the open, standards, Linux, whatever that gets out there. So all that I talk about is going to be push upstream. And if you want to talk about it, I'll be here for the day. We can talk how to, give you early access if you really want that, or what's the roadmap. So if you have any questions, I'm happy to take them. The question is, I'm with Samsung and I have not listed firmware update as a use case. I believe firmware update falls under NVMe in itself. So you have ways of updating firmware on the fly, and CNS is not any different than, it's a new firmware on this. We even ship same devices with a different firmware. So the question is, nameless writes have been brought up several times. Why this time is different? So I'm not a big fan of append command. So I'm not a big fan of it because it introduces a lot of changes to, to the whole stack. It's something that is being pushed into the standard. There are a number of vendors that really want it to happen and see it as a solution. I believe that this time, if somebody really wants to use this archival use case and they have the right file system and they have, I know of some people that are implementing that. It fits their architecture. I do not see it as a mainstream thing. I believe that solutions like the some random write area are much easier to implement, are much easier to manage. So I don't know if it's going to catch up, but I'm not very optimistic about it, if that makes sense.